In this video, I'm going to talk about how, after inspecting data during training, my conclusion is that independent sequence packing using the flash attention var_len function seems to be the LLM Foundry default, whereas using BinPackCollator does naive sequence packing, which is not what we want because that contaminates the attention across multiple sequences. So here are my main takeaways with a large asterisk, whether, if I understand this correctly. So keep that in mind, and if you are an LLM Foundry expert and something I say is wrong or there's a solution to something I'm saying, please comment below. So first takeaway is that LLM Foundry by default uses the flash attention var_len function, which, as the name suggests, allows for variable lengths sequences in the batch, so you can basically reduce or eliminate the use of padding tokens and do attention for each independent sequence. And this is triggered by the attention mask being not none, which we'll see later on as well. Second takeaway is that using BinPackCollator introduces contamination across sequences. So even though it does correctly pack sequences into a single item from the whole batch, when you perform flash attention on it, and as you prepare all of the artifacts that are arguments to the flash attention function, we can see that it's handling multiple sequences packed into a single sequence, and then it's going to take attention on that single sequence that has multiple sequences in it. So one sequence is going to be able to quote unquote see the other sequences that it's been packed with, and that's the behavior that we don't want. We want each sequence to be treated independently. If we don't use BinPackCollator and we are using the fine-tuning train data loader, LLM Foundry by default seems to use the sequence-to-sequence fine-tuning collator, and this maintains boundaries between sequences, treating them independently in the cumulative sequence lengths object that gets passed on to the flash attention var_len function. So my conclusion, based on what I understand today, is that don't use BinPackCollator. LLM Foundry handles sequence packing already on its own by default. So let me show you why I came to this conclusion, and hopefully I present a decent case. So the first thing is we want to confirm which function is actually being used in terms of the flash attention interface. So for that, I have this data inspector, and I have a previous video that I have made on the details of how I built this data inspector. But inside the data inspector, I have this after loader event handler, or after data loader event handler. So after the data loader is created, it runs this function. And here I'm just logging a bunch of different items. And one of the things I log is I look at the model, look at the first layer, look at self-attention in that layer, and I look at the forward pass. And then I'm using the getSource function from the inspect Python built-in package and converting that to a string, and that's going to be printed out. So here's what it looks like. This is the printed out text that I put into Markdown, so it looks a little prettier. But inside this self-attention.forward, because I'm using a Hugging Face model, the small LM2 135 million parameter model, I can see that it's calling flash attention forward, and it's giving it query states, key states, value states, attention mask, etc. So if we go to the flash attention forward method in the transformers library, we can see that there's a couple of places where flash attention var_len func is used. One place is if attention mask is not none, then it calls the upad input function, and that creates the values that are going to be sent into the flash variable length interface as these input parameters. So that's one function that's of interest, this underscore upad underscore input. And then if you scroll down, there's another scenario where flash attention forward, it also calls flash attention var_len func, and it uses the prepare FA2 from position IDs to prepare the flash attention input arguments. So these are two functions. So upad input underscore upad underscore input and prepare FA2 from position IDs, those are two functions of interest. And if I can see that LLM Foundry through my Hugging Face model is calling either of those two functions, then I can confirm that LLM Foundry is using flash attention varlen func. And again, the reason I want to use the variable length flash attention function is because I want to pack sequences together so that I don't waste compute on padding tokens. So this is a summary of, or first iteration of how I monkey patched the UPad input and prepare FA2 from position IDs functions with the help of Claude. And this all takes place in LLM Foundry's command utils train.py, which is the main training script where the trainer is built and trainer.fit is called. So first, I import the module that I'm interested in, and that's transformers.modeling flash attention utils, which was where this code comes from. So I import that as flash utils. I save the original functions as original UPad input and original prepare FA2 from position IDs. And then I define the two new functions, debug UPad input and debug prepare FA2 from position IDs. And they take some positional arguments and keyword arguments, and they return the original function given those arguments. And then I replace UPad input with my debug version, and then I replace the prepare FA2 from position IDs function with my debug function. So this is how I've monkey patched these two functions so that in this case, this was the first iteration, I would print out the statement debug, it's using UPad input, or debug, it's using prepare FA2 from position IDs. So when I ran the training script, if I saw this debug line, that to me was confirmation that UPad input or prepare FA2 from position IDs is used. And if we go back and look at the actual usage of these functions, that means that if those two functions are used, one of those two functions are used, that means the variable length flash attention function is used. So that was my logic, and that's what I've done in terms of monkey patching and adding these debug statements. So over time, I wanted to look at and inspect different items inside UPad input. So I added a bunch of print statements. First thing is I want to look at the input arguments to UPad input. So there's query states, key states, value states, attention mask, and query length. Then I'm actually calling the original UPad input so that I can inspect the output values that get passed on to the flash attention varlen function. And then I'm looking at their shapes. I'm looking at some values in total. So I'm looking at the cumulative sequence lengths as a list. I also then later added a get unpad data's sequence lengths in back, which I'll talk about next. But the main idea here is that once I have monkey patch one of the functions, I can add in whatever I want to inspect, whatever artifacts that I need to. And the key thing is at the end, we return the original UPad input with the original arguments so that we're not messing up the actual calculations. Okay, so first we're going to look at the scenario when we are using BinPackCollator. And then second, we're going to look at the scenario when we're not using BinPackCollator. So BinPackCollator, again, is one of the sequence packing methods in LLM Foundry. And the way you activate it is that two things have to be set in the train loader, in the training YAML file. First, the name has to be set to fine-tuning, just one word. And inside dataset, the packing ratio has to be set to either something greater than 1.0 or the string or the name, the text auto, AUTO. So either one of those packing ratio values along with the name being fine-tuning is going to trigger the particular fine-tuning data loader that uses BinPackCollator as the collate function. So when I ran this training with this particular YAML file and I looked at my data inspector callback logs, I could see that the collate function is indeed BinPackCollator. And if we go a few slides back, here's the collate function, and I'm looking at state, data loader, collate function, base collator. So that's the function name that we're looking at here. And so I'm just confirming that, yes, indeed, I am using BinPackCollator. Okay, so now we look at some more interesting things. I have 4 items in my batch because my batch size is 4. So I'm looking at item 0, item 1, item 2, and item 3. And in each case, I'm looking at the number of padding tokens and the number of non-padding tokens. And this is where BinPackCollator's efficiency comes in. It's going to pack multiple sequences into a batch item, and so it's going to reduce the number of padding tokens that are used. So inside here, there's 1,946 non-padding tokens. In the second item, I have 1,876 non-padding tokens, and so on. And if you want to look at what that looks like in code, go back to my callback. Here's non-padding tokens for item 0. And I'm basically iterating through the input IDs. And if the input ID value, element value, is not 0, then that is a non-padding token. Because for small LM2 135M, the EOS token, which is the padding token, is token ID 0. So if the elements are 0, they're counted towards padding tokens. If elements are not 0, they're counted towards the non-padding tokens. Okay, so that's my first check, first understanding and inspection that this is what BinPackCollator is doing. If I look at the actual decoded text, which is again just another line in my callback, I can see that there are 8 end of text tokens that are delimiting 8 sequences. So one batch item has 8 sequences, and this is how we're maximizing the maximum sequence length, or the sequence length, in the batch item by packing in multiple sequences together. All right, so now I'm going to look at the UPad input, debugging, print statements, and different shapes and things like that. And things that jump out immediately are the cumulative sequence lengths. So here, because I have 4 items in my batch, I'm going to have 5 items in the cumulative sequence lengths object. The first item is 0, that's the start of the batch item. The second item is how many non-padding tokens there are, plus the end of sequence tokens at the end of each of the packed sequences. So that's 1954. Then we have the second batch item, third batch item, and fourth batch item. So if we look at the get unpad data, this is what is used to calculate the cumulative sequence lengths. And what it does here is that it takes the cumulative sum of this artifact called sequence lengths in batch. And if we look at sequence lengths in batch, it's taking the sum of the attention mask across the last dimension. And we'll see later on in the second section of this video what that looks like. So if I look at get unpad data's sequence lengths in batch, I can see that the first item, so the first sum of attention mask elements, which corresponds to batch item 1, is 1,954. And if I look back at my non-padding tokens value, that's 1,946. So there's 8 more tokens, and those 8 tokens are the EOS tokens at the end of each of my 8 sequences that are packed into this batch item. So at this point, I'm just kind of making sense of everything that's going on. But after thinking about it a bit more, I realized that if I understand this correctly, it's considering the 8 pack of sequences as a single sequence, right? So cumulative sequence lengths, the first sequence goes from 0 to 1954, the second sequence goes from 1954 to 3835, and so on and so forth until the final token, which is at position 5151. So the fact that the first sequence is 0 to 1954 means that the first sequence is actually 8 sequences. And so when it's going to calculate the attention scores across the sequence, it's going to look at the attention score from tokens in this first sequence, and then they're going to have attention scores for all these other tokens in all these other sequences. So based on this, and based on my understanding of attention scores, this is going to contaminate the data in the sense that one sequence, so the lights in Malcolm's house are flickering, the answer is 3. That sequence is now going to attend and be attended to by the other sequences in the batch item, which is not what we want, right? Because when we're doing inference, we're going to provide a single question. We're not going to provide a pack of 8 sequences with the assumption that the model should look across those 8 sequences and make relationships across those sequences. These are question answer, math question answer items. If we do present this information as a batch, we want each of the sequences to be attended to in and of themselves independently, not across multiple sequences. So that was kind of my first, understanding of how BinPackCollator, while it seems to be doing sequence packing, because LLM Foundry is using flash attention varlen func, it's not going to work in our ideal way. And the last visual in this section that we'll look at is just looking at input IDs versus labels. So this yellow highlight text is the answer or the response to the first question. And if we look at the labels, we have the yellow highlighted response that's packed next to the pink highlighted response, which is the response to the second item. The green highlighted response is the response to the third item. The blue is the fourth item, and so on and so forth until we get, 8 items in this batch item. So that's just another visual to look at how we have multiple sequences packed in together. And if it's handling this 8-pack of sequences as a single sequence, we're going to have contamination across the boundaries of the sequences. Okay, so that's when using BinPackCollator. Let's look at when BinPackCollator is not activated. So this is the default LLM Foundry behavior when you have your trained data loader having the value of name being fine-tuning. And it turns out that it uses the sequence-to-sequence fine-tuning collator as the default collate function for this fine-tuning data loader. So again, here's my YAML file. I still have the name of fine-tuning under train loader, but I have commented out my packing ratio, so it will not trigger BinPackCollator. So here's confirmation visually that the collate function is in fact not BinPackCollator, and it's the sequence-to-sequence fine-tuning collator. And here's a reminder again that I have monkey patched the UPad input, and I'm printing out these intermediate artifacts that eventually get passed on to the flash attention varlen function. Okay, so first things first, when I run training with this default behavior, I see that the using UPad input debug print statement has appeared in my logs. So that lets me know that even without specifying BinPackCollator, so even without specifying a packing ratio, LLM Foundry is using the variable length flash attention function. So that was interesting. I was not expecting that, and that led me to dig deeper along with my research group members on what this behavior is. So if we look at the items, the 4 items in our batch, 0, 1, 2, 3, if we look at the number of non-padding tokens, now it's much less. So out of 1048, I only have 200 non-padding tokens, right? Because this is not sequence packing. This is padding tokens to the maximum sequence length specified, which is 2048. The second item is 177, third item is 224, fourth item is 396. And if we look at the sequence lengths in batch item, we see that each item here has one more token, and that's the EOS token at the end of the sequence. And if we look at cumulative sequences, it matches these numbers as well. So we go 0 to 201, 201 to 379, which is 178 more, which is 177 non-padding tokens plus the EOS token, up to 604, and then up to 1001. Now, if I would have added more items to my batch, this would have kept going and tried to fill out the maximum sequence length of 2048, which is my understanding right now. And how do I know that the final token is actually being included? Well, if I inspect input IDs of that first item, so here we have 200 non-padding tokens. So show me where input ID is greater than 0. I have 200 elements here. And then show me where attention mask is equal to 1. I have 201 elements. So that lets me know that the attention mask is including the final EOS token, which is why it's being included here in the sequence lengths in the batch. But what this means is that based off of my understanding of cumulative sequence lengths, the first sequence is strictly one sequence, right? it's the first 200 tokens. The next sequence is the next 177 tokens in the batch. The third sequence is the next 224. And the last sequence is the last item in the batch, which is a single sequence with 396 tokens. So this tells me that this is correctly treating each sequence independently, and each sequence is not going to attend to or be attended to by other tokens and other sequences in the batch. And so we're not going to have that contamination across sequences. That's my understanding from looking at this. And if we look at one of these items, we can clearly see that there's very few tokens that correspond to the actual math question. And then the rest of the tokens, we have a wall of EOS tokens. Okay, so I'll end again with my main takeaways. So LLM Foundry by default uses the variable length flash attention function. And that's because attention mask is not none. When we use BinPackCollator, it introduces contamination across sequences. And we see that because the cumulative sequence length object includes all 8 sequences in the first sequence. And by default, when we use the LLM Foundry sequence-to-sequence fine-tuning collator, so there's no packing ratio, it maintains the boundaries between the sequences, treating them independently in our cumulative sequence length object, which then gets passed on to our variable length flash attention function. So my conclusion, even though I was very excited about BinPackCollator in a previous video, I have to backtrack that. And for now, my conclusion is don't use BinPackCollator because variable length flash attention is already being handled and we don't want to attend across sequences when we're calculating attention scores. So that's it for this video. Let me know if you have experience with using this and have understood it differently. Please comment below. Please like, subscribe, etc. Thank you for watching, and I will see you in the next video.